Good morning, everyone. My name is Rohit Puri. I'm a network engineer at Meta. Today, Hany and I are excited to share our story behind the evolution of Meta's AI network, one of the world's most advanced network infrastructure built to power generative AI. Let's first talk about the motivation. We have been driven to design, build, and operate the ever larger networks, not only to support the exponential growth of AI for our current use cases, but also for the long term vision of artificial general intelligence and superintelligence as defined by our leadership. As you can see in the chart, we have grown our GPU interconnects 100x scale since 2023. Hany and I would be going through some of the preview of challenges that lie ahead of us in 2026 as we scale up even further beyond 100K plus clusters. With the motivation, let's talk about the basic building block that we use in network AI. This is a basic building block that we use as our infra called an AI zone. As you can see, it's a simple two-class topology. It is hosts, which are GPUs connecting to a TOR switch, which we call an RTSW, which connects to the spine, which we call a CTSW. Over the period of time, we realized that the AI work models are very sensitive to the bandwidth between the RTSWs and the CTSWs. So we intentionally undersubscribe these links to add more buffer for any maintenance and drains that can happen during the normal course of the DC operation. This continues to keep our performance intact and robust operations throughout the training. As you can see also, this AI zone can accommodate from 2K to 4K GPUs. The AI zone sits in a DC building. This DC building is what we call a standard Meta's DC deployment called DC Type 1. So you can see, basically, this DC has 4 data halls in it, and each data hall can have up to 2 AI zones. This makes it up to 8 AI zones possible that we can fit into this data center. There is an MDF, which does the network aggregation, and then there is a core BDF, which connects all the interconnects for the data hall. With this basic introduction, let's go over today's agenda for the talk. We will be delving deeper into the network architecture evolution for GenAI. Then we would go through the challenges and the lessons that we learned as we started to ramp up the traffic in the cluster for 100K plus cluster turnup. And of course, then we will go through the conclusions and outline of what lies ahead of us in 2026. With this, I would like to hand it over to Hany to talk more about the various network builds we have done over the period of time for network AI.
Thanks, Rohit. Let's keep in mind some of the keywords that we just heard from Rohit's introduction, as these will keep coming up throughout the presentation today. All right, let's dive in the first cluster that we built for generative AI. This is what we call the 24K cluster. We built this network in 2023, specifically for training Llama 3. As we see in the drawing, here the network occupies one data center building of 4 data halls. We really wanted to pack as many GPUs in this one building as we could. So what we did is we removed any non-AI servers from the data center, and we deployed 2 AI zones per data hall. We called this the CRAM approach, and it resulted in 8 AI zones in this one data center. All right, so now we have 8 AI zones, and we need to interconnect them. So what we did is we installed a super spine layer in the BDF that we see here in the middle of the drawing that we call the ATSW. This aggregation tier resulted in 24,000 interconnected GPUs. While this 24K cluster served its purpose for Llama 3, next gen generative AI models demanded greater GPU scale. So now this brings us to the 100K plus cluster. Let's take a look at that. All right, this is the 100K cluster, the 100K plus cluster. And the first thing that we notice here is that it's multi-building, right? So this is actually one important takeaway in the evolution of Meta's network infrastructure for AI, the transition from one building to multi-building. This is a type 1 region comprising 5 buildings. Each building houses 4 data halls, bringing the total to 20 data halls across the entire region. Similar to the 24K cluster, the previous cluster that we just looked at, we followed the CRAM approach here, and we deployed 2 AI zones per data hall. As we see here in the drawing, DCs 2, 3, 4, and 5 are fully populated with 8 AI zones each, while building 1 only has 6 AI zones and 1 data hall dedicated to support and services. Support and services include storage servers that feed the data set to the GPUs. In total, here we have 38 AI zones, bringing the total scale of GPUs to over 100,000. This actually makes it one of the largest AI clusters in the world. Right now, we will zoom in and we will take a deeper look at the network topology per building. All right, we are now looking at the topology of one building. We are zoomed into one building. What do we see? We see 4 data halls. We see 2 AI zones per data hall. The AI zone is exactly what Rohit just showed us earlier. It's a 2-stage claw topology with RTSWs connected to the GPUs and uplinked into a common set of CTSWs. Each and every CTSW in the data center uplinks to a core layer of 76 ATSWs. The ATSW layer here plays 2 roles. Number 1, it interconnects the 8 AI zones within that one building. And number 2, it connects this building to the other buildings in the region, providing regional connectivity. It's also worth mentioning here that for one AI zone to cross the ATSW layer and talk to a remote AI zone, it will have to go through oversubscription of roughly 3 to 1. All right, now let's take a closer look at that regional connectivity that we mentioned. The regional network is constructed by fully meshing ATSWs of the same index across all 5 buildings. What does that mean? For example, ATSW1s, right, from all 5 buildings are connected together in a full mesh. ATSW2s connected together in a full mesh, and so on. Right, all the way to ATSW76s. This creates 76 distinct and orthogonal planes that are represented here in the drawing with the purple rectangles. Within each plane, a given ATSW uses 144 uplinks distributed evenly across the other 4 ATSWs in the plane, with 36 links to each. It's worth mentioning here that the fiber infrastructure between the buildings is based on OSP, or outside plant fibers. And the physical distance between a pair of GPUs across the region may reach the range of 3 kilometers. All right, now that we have a basic and fundamental understanding of this 100K plus network, let's see how we used it to support generative AI services. All right, the one important thing to note here is that the 100K plus cluster was used to train and deliver Llama 4 earlier this year. Initially, we trained Llama 4 with 32K GPUs put together simultaneously. Then we pushed the boundary and we placed roughly 100K GPUs in the same workload. Right, that's definitely a massive AI workload. Imagine 100,000 roughly GPUs talking together, exchanging gradients at the same time. Right? So definitely here we need to take care of performance and throughput. Right? So we did two things to boost performance in such a massive workload. Number one is we invested in optimizing the communication library for cross-building traffic. Number two, we used a combination of different parallelisms that are resilient to the latency profile within this large network. All right, now we go back to Rohit to talk about the challenges that we experienced when bringing up this 100 plus K massive network.
Thank you, Hany. That's really a great design, but we still expected some challenges as the GenAI workloads start to ramp up on this network. So we took some proactive actions to address those challenges. The foremost challenge that we knew we were going to run into would be the large amount of network congestion. We know with the scale increase and the bursty nature of the AI traffic, there is going to be increase in the bandwidth at all different layers of our network. Further, we rely on priority flow control, which is PFC, for maintaining the lossless environment or lossless network. This actually leads to a potential for head-of-line blocking. We obviously don't want to be in a scenario where we have large queue buildups resulting in huge tail latencies and deterioration of the performance of the models. One of the first actions that we took was to put deep buffer switches on the CTSWs. The idea has been that they can absorb the congestion without actually PFCing the other side, and hence preventing a potential for head-of-line blocking. The second thing what we did was to actually tune the thresholds to be very aggressive on the RTSW so that we PFC rest of the network as less as possible. The second issue that we ran into, as Hany also talked about, has been the long distance. As we went through, there are 5 DCs in the 100K plus cluster, which are spanning over 3 kilometers. Now, there's not a lot we can do about in terms of the distance, which results in higher propagation delay and more time delays to the model. But what we did was we cushioned some of these effects by developing low latency special settings on our spines, working with the vendor and deploying them specifically targeted towards our use case. Last but not the least, we didn't expect that everything will go per plan. So we invested heavily in debugging. We wanted an ability to debug, isolate, and mitigate a problem very quickly in the network as quickly as possible. So we invested heavily in monitoring and creating the dashboards, which would give us the network health metrics at all layers all the time. Now, when we started to ramp up the traffic, we still ran into problems. I mean, I didn't expect there will be no problems. But this problem was pretty interesting. We started to drop traffic as we started to ramp up at higher GPU scale. We had drops at the RTSW layer. Now, to maintain a lossless network, we would generally have 2 queues, a lossless queues and a lossy queues. We started dropping in lossy queue, which is kind of expected. But what was interesting about this problem was that lossy queue carries actually less than 1% of the traffic. The bulk of the traffic actually is the rocky traffic, which is going in the lossless queues. But why would this be a problem? We were carrying some special control rocky packets in this queue, which also started to drop, and hence it degraded the workload performance. So the fix was actually pretty simple in a way. We moved all that rocky control traffic back into the lossless queue so that it won't get dropped, and also tweaked the buffers in such a way that the probability of we dropping even on this lossy queue actually goes down quite a bit. Once we made these fixes, we were actually able to move forward. We went a little bit farther ahead in our scale when we started hitting drops, and this time with the spine layers. We actually saw this at intermittently happen. The scale was very high, which was a challenge, and this problem wouldn't reproduce itself all the time. But when we debugged this with the vendor, we found that this was actually an unprecedented scale which was causing this problem. We had concurrent traffic coming at high speeds from all the ports from the different directions. And at the same time, RTSWs were heavily PFCing the CTSW, which resulted in a contention of buffers causing drops. We devised a plan to fix this problem, and the fix was actually rather simple. We actually detect this situation and PFC back into the network when this happens, mitigating the transient congestion. We deployed this fix in one of the DCs, monitored the performance just to make sure there's no side effects, and then rolled it out into the rest of the fleet without any downtime as the jobs were ramping up so that we don't block the models. Once we made this fix, we were actually able to go farther ahead with mostly running smoothly when we ran into our third problem. This was kind of an interesting problem for us because what happened was that we were running an 8K GPU job, which was running across multiple DCs, but then one of the DCs, which was DC number 1, actually showed 30% degradation of performance. Now, what made this challenging was several-fold, actually. There were 8K GPUs that were needed at least to reproduce the problem. It wouldn't happen at a smaller scale. We would monitor the metrics that we monitored, did not point to any problems at all. And last of all, there was a new NIC firmware here, which was also put in for the optics support in this DC. It turned out that the new NIC firmware version had divergent settings from rest of the fleet, which actually caused some regression. Once we found that and fixed it, we were able to recuperate about 10% of the performance. But there was more problems. We actually found that one of the NIC monitoring tools that we had put in actually caused a polling on the CPU, which would cause a contention and drop in the NIC throughput. Once we actually disabled that monitoring and fixed it, we were able to reclaim this back. There were several other problems we ran into, but I think the key here was for us to be able to isolate the problem, detect it, and mitigate it quickly. With this, I would like to hand it over to Hany to go over the conclusion and the outline for what lies ahead of us in 2026.
Thank you, Rohit. We are coming to the last section in our presentation today. All right, let's take a few takeaways from this talk today. Right? The first takeaway is model complexity is increasing. Demand for power and GPU scale always on the rise. The second takeaway is that our network had to evolve proportionally, right, to meet the increased demand by the AI models. So if you look at the drawing here, before generative AI, we used to deploy standalone AI zones mapped one-to-one to a data hall. Right? We evolved from this to a whole building network, like the 24K cluster that we went over. Then we evolved again from one building to multi-building, to a whole region interconnected. Just as we saw with the 100K plus cluster. As we grew, challenges emerged. Rohit went over how we mitigated serves and issues around latency, oversubscription, and congestion. All right, so what's next? So our next milestone is Prometheus, and we are very excited about that. This is a super cluster that will span an entire metropolitan area and will have a number of sub-regions connected together with a regional aggregation layer. We expect that the GPU scale will become in the hundreds of thousands, may even cross 1 million. We know and we expect that there will be new challenges with the increased network diameter. Right? For one, we will need to train our models over very, very large distances, probably over 100 kilometers. We also will have heterogeneity of GPUs and accelerators, variety of NICs, variety of switching platforms in the sub-regions within that metropolitan area. We love solving complex problems. That's what we do at Meta. So we are incredibly excited about the future. Thank you for listening to our talk today, and hopefully that you enjoyed it.